Last time we saw our MOSFET power module, it had a frequency response problem. The gain almost doubled at 48 kHz, and I think that could cause me some trouble. While I didn't have space for a high-pass filter in the drive loop, I did have space for a low-pass filter at the input, before the feedback enters the equation. So I decided to put a 20 kHz RC filter at the input. Of course, that won't help with high-frequency noise in the drive loop, but it should help with noise going into the module. With the filter in place, the gain is now pretty flat through 16 kHz, then starts to drop ever so slightly, maybe down about 3% as I get into the low 20 kHz region. Just a nice smooth gradual drop as the frequency goes up. As I step up in frequency, don't seem to have any distortions or waveform problems. Just a lot of noise spikes in the waveform, and I will see if I can deal with some of them in a bit. And by the time I get to 48 kHz, gain looks to be down about 20%. I'm much happier with this. So I think it's time to get the ADC channels up and running and see what kind of noises I've got to deal with. This is a block diagram for the secondary processor core's ADC module. It's got a lot of stuff in it and a lot of registers to go with it, and this doesn't even show the triggering block. The plan is to use ADC core 0 and 1 to sample the voltage and current signals. Also, I hope to take advantage of the digital filters so I can have plenty of oversampling. But for right now, I just want to get the ADC module up and running. Here is how I have the ADC cores and digital filters set up. Starting with the digital filters, I have them set for 16 samples. So after 16 ADC conversions, the filter result will be placed in the filter data register and an interrupt will be generated. I'm triggering both channels, AN0 and AN1, from a timer. And right now I have the timer set to about 12 kHz. And now a bit of math comes into play, as I have to figure out what kind of ADC clocks I need to get 16 conversions complete in less than about 81 microseconds, or about 5 microseconds a conversion. From the datasheet, conversion time for a 12-bit result takes 8 T-core SRC clocks and 14.5 TAD core clocks. To that, I'll add the 9 TAD core clocks from the conversion delay settings. These 9 TAD core clocks will be the sampling time for the sample hold capacitor. Even though the T-core SRC at a maximum is half the clock time of a TAD core, I'll add all the clock times together to give me a starting point. If I take the 5 microseconds and divide it by 31.5, that will give me a TAD core of about 159 nanoseconds. And that is very close to 6.25 megahertz. And 6.25 megahertz is an easy number to work with. The FOSC over 2, the instruction clock, is 100 megahertz. Run that through the clock source divider set to divide by 4. That will give me 25 megahertz and a T-core SRC clock time of 40 nanoseconds. Then I'll set the core 0 and 1 clock dividers to divide by 4. That will give me 6.25 megahertz and a TAD core clock time of 160 nanoseconds. So 8 times 40 nanoseconds plus 23.5 times 160 nanoseconds gives me 4.08 microseconds per conversion, which gives me 16 conversions in about 65 microseconds. So should work fine. Bit of dead time in there, but this is just to get things running. At least running enough to help me determine what noise threshold I can tolerate. So off to noise hunting. What noise to tackle first? There are so many. There is one higher frequency noise that seems to be on all the power rails, but most predominantly on the 12-volt rail. So this is the first noise problem I'm going to try and tackle. This is on the 12-volt rail, and of course my first thought was, what's happened to my power supply filtering? This is almost a 3-volt peak-to-peak signal. But this switching noise is around 85 kilohertz. The power supply is running at 130 kilohertz. and it's not coming from the fans. They are not on at the moment. I thought I just don't have anything switching at 85 kilohertz, and I thought about it some more, and then I smacked myself in the forehead. There is another switching regulator, and this is it, on the display board. And as soon as I pulled up the schematic and saw the 4.7 microhenry inductor, it all came back to me. 4.7 was the largest I had on hand when I was putting this together, and would work well if I was pulling an amp and a half or so. I'm pulling maybe 100 milliamps. I think I figured I needed around a 47 microhenry, and I remember ordering some. I also ordered some 10 microfarad 50 volt caps to go in C19 here. What's in C19 right now is a 10 microfarad at 16 volts, which makes it maybe a 1 microfarad capacitor when it has 12 volts on it. I should have put a post-it note on the display board saying, "Update parts." It's working. Output is 3.3 volts. I didn't even check at the time to see what the consequences of using a smaller inductor were. I just put on my to-order list the 47 microhenry 1210 case inductor and a 10 microfarad 50 volt 805 case capacitor. Then weeks go by before I get back on it. It's working, so I forget where I left off at, or even that the new parts had arrived. Now with the proper inductor, the 12 volt rail right at the regulator on the display board looks like this. So much better. Frequency is up around 700 kilohertz, where it should be, and only about 400 millivolts on the 12 volt line. Probably would be okay, but I do want to put the correct capacitor in place. 16 volt rated cap is not really good enough for a 12 volt supply. I do want it to last more than a year. It wasn't a month ago I was getting a capacitor out and thought, what did I order these 10 microfarad 50 volt 1206 case caps for? Turns out they were for this. I didn't see any 805 case capacitors that retained half of its capacitance at 12 volts. So I ordered the 1206 case and figured I would just squeeze them in. Well, squeezing a 1206 into an 805 space, I should have searched more. Probably could have found a good 805 capacitor. I'm going to put one across the power pins feeding the board. I think that will be okay. Being sorted to the pins and not on a pad may be a bit too much stress in the long run. And I will replace the C19 cap with the 1206 case capacitor. 805s just look tiny compared to the 1206s. At least I could get it to share a pad with the other capacitors. Even though these are 50 volt caps, with 12 volts on them, it still takes 2 to get me to 10 microfarad. And now the 12 volt rail, right at the regulator, looks like this. The very thin spikes, I suspect may be noise picked up by the scope probe, and not really on the 12 volt rail. But the voltage ripple is less than, say, 20 millivolts now. I think I could have gotten away with just the one 10 microfarad cap. But I'm hunting noise and quashing, and I think I've got one noise source under control now. I did make space for some extra inductors and capacitors around the linear regulators on the main board. I'd not put the parts in place, wasn't sure if they would even be needed. But if those very fast spikes are on the voltage rail and not just an artifact, I think putting the inductors in place would be a good idea. I will also go ahead and put all the capacitors in place. This is what my plus 5 volt rail looks like now. The gain on the scope is wide open. I don't think that is too bad. This is the 1.2 volt band gap reference voltage. It runs off the 5 volt line, so maybe that's why they look quite similar. This is the negative 5 volt rail. This is the only one I didn't make space for an input inductor. And it does look like some very fast spikes may be getting through. That makes me think those spikes are present and not an artifact. And now the 3.3 volt rail. A little more noise, and I'm sure some of it is coming from the processor itself. I have both core clocks running wide open. The noise is not at any higher frequency than the other supplies. I've slowed the scope sweep down here. You can see what looks like a tiny square wave in all the noise. The thing is, it looks to be right at 60 cycles. I'm not sure where the power line frequency is getting in here. At about 5 millivolts, I can't see it being a problem. The high frequency noise does kind of swamp it out. And now the voltage that goes to the AVDD pin of the microprocessor. The voltage that powers the ADC circuit. This is not near as clean as I was hoping for. and that maybe 5 millivolts 60 cycle that wouldn't be a problem on the main 3.3 volt rail could be a big problem here. The least significant bit of the 12-bit ADC should have a sensitivity of less than 1 millivolt. I'm not sure what I can do to clean this up. Finally, this is what I get with the scope probe tip shorted to the end of the ground spring, touching ground on the PC board. So a lot of the noise I'm seeing on the voltage rails is not really there. And there is even a bit more complications. I did try to separate the digital and analog ground planes. This being the digital area, with the closest connection to the power grounds coming to the board. And then this ground plane is where all the analog parts ground to. The path that connects the two planes is this one large trace. It starts right at the ground terminal of the 3.3 volt linear regulator and ties to the analog plane right at these 4 vias. All the previous waveforms were referenced to digital ground. I wondered if I could see any difference between digital ground and analog ground. And this is the waveform referenced to digital ground with the probe tip on analog ground. I was a bit surprised. That 5 millivolts of 60 cycle being across the two grounds, I just would not expect that. It makes me think I have a ground loop somewhere. And ground loop hunting is not fun. But the ADC in the microprocessor is not referenced to digital ground. It has its own ground pin, AVSS, and that ground pin is connected to the analog ground plane. And I have a capacitor very close and right across the analog supply pins to the microprocessor. And this is the waveform right across that capacitor. It is basically the same as if the probe tip was shorted to the ground spring. I think the 3.3 volt analog supply to the ADC is going to be fine. And finally, the waveforms at the ADC input pins. I do have the current load terminals shorted for this. First, the ADC input for the voltage sense. From the input terminals, it goes through a resistor divider and then an op-amp buffer. So I think that looks pretty good. Now the ADC input for the current sense looks very similar, but the waveform has a bit more noise amplitude than the voltage input. But this signal is from the current sense amp that is sensing the 1 milliohm current shunt, then goes through an op-amp with a gain of about 1.1, and then to an op-amp buffer. I'm quite sure the noise increase is coming from the current sense amplifier, but I will have to deal with that noise in a future episode. Thank you for watching.